Okay.
Okay, so let's begin. It's a pleasure for me to introduce Chris Granade, who I've known for quite a while now. We were both students at the Institute for Quantum Computing, where we both obtained our PhDs, and we actually were both at one point at the University of Sydney as postdocs. Uh, so it's been great to yeah, have Chris as a colleague all around the world, and now virtually. So Chris will be telling us about quantum machine learning research, particularly with the Qsharp programming language. So take it away, Chris.
Well, thanks, and thank you very much for having me here. As you say, it's been really an honor to know you and work with you for all these years, and it's great to come back virtually to talk a little bit about what I've been up to at Microsoft. So with that, I want to kind of set the stage a little bit, with why talk about quantum development? What makes quantum development interesting? How does it connect back to research? And there's a few different ways I see that. One is when we talk about algorithms and applications, we really need to be able to have some practical kinds of cost estimates to understand those algorithms and applications to compare against. There's been some really neat research over the years about not just asymptotic improvements, but what the constants are and things like that. Trying to understand that through cost development, though, is a really neat tool. So the example I always come back to for that is quantum chemistry. If you look at examples like ferredoxin, at one point, the best known classical algorithm was simply intractable, that, age of the universe kind of thing, whereas the best known quantum algorithm took under fairly reasonable cost estimates about 3,000 years to complete. Improving the algorithms and doing a more careful cost analysis using quantum development, using quantum programming, improved that 3,000 year estimate down to about 1 day under the same cost assumptions. So it gives us a much more practical understanding of what it would take to solve this problem using quantum computing. But another really important one is debugging. It's really hard to debug quantum algorithms, especially if you can't run them. And there's a lot of value in running a quantum algorithm and getting the wrong answer so that there's something wrong and you can go back and fix it. We understand from classical programming and classical development that there's immense value to things like unit tests and integration tests that allow us to check whether or not a classical program actually meets assumptions that we make about it, if it's actually doing the right thing. So when we write out a quantum program in a way we can run it, that lets us test our expectations about what that quantum program does. But the one that is always really near and dear to my heart is when we write out quantum programs, when we develop them explicitly, we move from algorithms to applications. So in particular, kind of the theme to all of that really, I think, sets the stage for me is that quantum development is something that lets us explore research ideas using what we've learned from classical computer science and from classical software development. So the example that I'd like to go into today is, as right up there in the title, quantum machine learning, and in particular an example called the QCC classifier that you can check out on the archive there. So if you run it, for instance, on a half-moon dataset, this is a nice synthetic dataset that's often used for benchmarking classification problems. You get this nice decision boundary out, and you can, plot out and understand how it separates those two classes. Today, I want to show how you can use Qsharp to explore that as well and understand quantum classification and as an example of understanding quantum machine learning. So with that in mind, the goal in this example, we're given some training data that some set of vectors, each of which some set of vectors of real numbers, each of which having a label either 0 or 1. And our goal is to find a function such that when we evaluate that function on the training data, we get the right label for as much of our training set as possible. The QCC classifier uses a quantum program to implement that function f. So in particular, that program consists of preparing the L0 state, running a unitary that depends on that vector x being evaluated in some way, applying another unitary that depends on model parameters. And that's the thing where we'll train our classifier to do it to separate out the two classes. And then we'll call that sample a 1 if measuring the last qubit after both of those returns at least 50-50 probability. And we'll also allow ourselves a bias away from 50-50 in order to separate those two classes. So informally, what we're doing here is we're picking a quantum program and we're running it many, many times, measuring the first qubit after each run to build up an estimate of the frequency with which we observe a 1 and use that to estimate our label. So to train that, we need to find the right parameters theta, the right model parameters to classify our training set. And so we can use variational methods to find those model parameters and then to find the optimal bias. So we'll take our input, we'll feed it through this quantum program, get an output, and use that to estimate gradients of our model parameters to improve our training. So let's break that down a little bit. So if we want to find derivatives during training, we can use ideas that came up out of, say, optimal control theory, like the Granade algorithm, to expand the derivative of that unitary, u theta, with respect to theta, in terms of derivatives at each different instruction in that quantum program. So there's a few things that'll make this simpler. If we start off assuming that each model parameter affects exactly one instruction in our classifier program, then we can write things out like this, where, let's see. All right, can you see the dot? Is that screen sharing?
Yes, it is.
Cool. So I can take the derivative of the output of this quantum program, and when I do that, I get by the chain rule, the real part of the overlap of the L0 state, V dagger, that's my input encoder, the derivative of U dagger, the Z that I use for the expectation, and then running on the right, I get the state that comes out of the classifier. I can expand this term here in terms of the derivatives of each individual instruction making up that classifier program. What's really neat is when I do this, the real part of that overlap, that can be evaluated using well-known characterization techniques. Here, for instance, the Hadamard test tells me about the overlap between two states, given copies of those states. And similarly, here, I might have that the derivative of a unitary, the unitary action of some instruction, isn't itself unitary, but I can decompose it into a linear combination of other classifier programs. So when I do that, and I go and implement this, let's see what that looks like in Qsharp to take that idea and run that variational algorithm in Qsharp. The first thing we'll want to do is do some classical pre-processing. So for instance, if I have the X and Y coordinates of those half moons we saw earlier, adding a product kernel that's the product of X and Y is a really helpful feature to feed into our quantum classifier. When I do that, I can then use Qsharp, the classical functionality built into Qsharp, to pre-process my samples to get something that's in a nicer form for inputting into my quantum classifier. I can then train using the quantum machine learning library that we released last month. Once I have those pre-processed samples, I can feed them into the train sequential classifier operation provided with that library. And when I do that, there's a number of different options that I can control as I call. So some of them are familiar to a classical machine learning workflow, such as the learning rate. So how much you multiply the derivative by each time you use that to do a gradient step. The mini batch size. So how many of the training samples do I use in evaluating each gradient step? as well as things like tolerance, what my stopping criteria is as I train. But then there are ones that look a lot more quantum, such as the number of measurements, how many times I have to prepare the classifier output and measure to get a good estimate of the label for an individual sample. Once I have that, I can then call into it fairly easily from Python. I can use that, for instance, with other Python tools like NumPy or the built-in parts of the standard library to load my data, my training data, feed it into the training operation and simulate that on, say, a laptop, a desktop, and get an idea how this works in practice on the quantum, if I were to run it on a real quantum computer. So with that kind of an example in mind, I want to break things down a little bit and see what components went into that classifier example that made it as easy to express there and that can help us explore QML ideas in research. And there's a lot of different pieces of the quantum development kit that go into that, from the language, libraries, to integration with different other tools, the development tools that you use as you write, and last but not least, the community of users and contributors who make the quantum development kit what it is. So now that you've seen a few Qsharp samples, it's probably best to go back and ask, what is Qsharp? So Qsharp really, I think of it personally in terms of an accelerator-like model, where I'll write programs that, you know, maybe run on the classical system, that I can write, you know, a host program in Python or C# or something like that. And then I can send my Qsharp programs over to one of several different target machines. At the moment, something like a simulator. So we provide a full state simulator, TOEFL simulator if you're, you have X and C naught gates, for instance, or the resources estimator to get resource counts, as we talked about earlier. I can use different libraries or as a part of that, but really it's this idea that I'm taking part of my workflow and running it that works best on the quantum computer, and I'm running it there using Qsharp. When I do that, that quantum program that I'm running, I'd like to think of it as really being a classical program, a special case of a classical program that has the side effect of sending instructions to a quantum device. So when I take that view, what Qsharp really is, it's a particularly nicely suited classical language for to the domain of working with quantum algorithms. You know, so when we one of the key points from that is that anything we then know or learn about classical programming helps us out here as well when we go to write quantum algorithms up in Qsharp. So let me take a really, you know, fairly basic example, because I think it's one where we can pull out some nice pieces from it. So writing out a quantum random number generator in Qsharp. So on the, I might do something like write an operation, next random bit that returns an individual result. And in that, I'll ask the target machine for a qubit using the using statement. And then I can apply an H operation to that qubit to prepare the superposition I need so that when I measure it, I get my 50-50 output. If I were to write that, you know, say in circuit notation or in Dirac notation or something like that, I might write things out a little differently. I might start talking about ket 0, or I might start talking about H applying to ket 0, and things like that. So let's take a little bit of a closer look to see what's going on here. The key difference between those two ways of writing out the quantum random number generator comes down to whether I think of qubits as being things which are states, so a qubit being a ket plus, or whether I think of a qubit as something that has a state, possibly a register of qubits having a state. And in Qsharp, we take the latter view. States aren't a part of the language. We instead think of passing a qubit to H, the instruction. And that means that then each target machine can define what a state is or define what a qubit is in an entirely different way. So if I run, you know, the classifiers we've seen so far on a local simulator, then that simulator keeps the state vector there, exactly as you're used to from anything else in quantum information, as an implementation detail inside the simulator. If I run things on a trace simulator or resources estimator, a qubit might just be a tally count of how many gates I've applied to it. On actual hardware, it might be an ID to somewhere on the device that I can use in pulse controls and things like that. But because I'm working with something that's an opaque qubit, my program works across all of these different ideas as to what a qubit is transparently. So I just want to underscore this, because this is where I think a lot of the power comes from. Quantum states aren't concepts in Qsharp. Instead, quantum programs written in Qsharp are classical programs that work by side effect. So this side effect is I send instructions like H or measure that affect the state through those side effects. When I'm working on a simulator or something like that, of course, it's always nice to be able to get the state out so I can work with and understand it. And we provide instructions like that that ask the target machine, whatever it is, to give the diagnostic information it has. And when it's running on a simulator, the state internal to the simulator is a wonderful diagnostic tool. So it's still there available to us as researchers, but making it not an object into language in this way means that the programs we write are portable across these different ideas of what a qubit is. And I kind of think of it a little bit like Heisenberg versus Schrödinger picture. So we'll often really want to pass states around when we start writing a quantum program. And so that seems to present a problem. How do I do that? If I look back at Heisenberg sort of picture, there I'm not talking about the state evolving, I'm talking about the operators evolving. So for instance, I just pick an initial state as a matter of convention, and then I talk about the operators evolving. So instead of talking about cat plus, I talk about H. Instead of talking about a bell pair, I talk about H then C naught. If I take inspiration from that, then I can really think of the idea of a state as it commonly appears in a quantum algorithm as being a program which prepares copies of that state. Since operations in first class values in Qsharp, I can pass those operations, those procedures that let me prepare copies of a state, as values. And so when I come back to the Hadamard test that you saw earlier in the QCC classifier, I can use language features in Qsharp like partial application to pass around the state that's prepared by my sequential classifier as an input to the Hadamard test. So here, for instance, is a snippet, and this is straight out of the QML library, where in order to evaluate the derivative at a certain point for a certain parameter, we'll use the Hadamard test provided by the Qsharp standard libraries as estimate real overlap between states. And there the states that you want to do a Hadamard test between are represented by two different operations that prepare copies of those states. In this case, we want to know what the state output from the sequential classifier is at two different values of the parameters of that classifier. And so we can do that by taking our model parameters so far and replacing the parameters with the model parameter vector by the point that we want to evaluate at. And that gives us the two states that we want to pass into that Hadamard test. Does that? All right. Are there any questions so far? All right. So what we saw there with the Hadamard test, prepare real overlap between states, is a great example of how the functionality provided with Qsharp, the Qsharp libraries, helps you out when you're writing out your algorithms in Qsharp. So that example comes out of the standard library, which provides a lot of the pieces you need, like characterization ideas, amplitude amplification, Hamiltonian simulation, a lot of the core concepts that you need in different algorithms. As well as there's more domain-focused libraries such as chemistry and numerics, and as of last month, machine learning that provides the QCC classifier we've seen so far. And all of those are library functions and operations that you can use in your Qsharp programs to write out your own operations and functions. So when I do that, all the Qsharp code that I write as a user lives in a namespace, and then I can open up the different namespaces that are made available by library to get access to the different functions and operations they provide. So for instance, if I want to do an X basis measurement and then reset the qubit using that measurement, I can use the mResetX operation provided by the Microsoft.quantum.measurements namespace in the Qsharp standard library. What's really neat about this is that, coming back to the theme that I mentioned earlier about we learn a lot from the history of classical development and classical programming, I can use those standard libraries to implement many classical programming ideas such as iteration to quickly write out different sort of circuit patterns. So for instance, if I want to do a C0 operation between each pair of qubits, one from each register, each of two different registers, that looks a lot like the zip function that you see in many different languages, where I take corresponding elements of a list and I make pairs out of them. Once I have that, I just apply C0 to each of those pairs, and I can represent that using apply to each. And that generalizes really well. So for instance, if I want to use the same two controls for each of a cascade of C0s, but change the target, I can pass the controls in, leave the target blank, and then I get something that I can apply to each different target. So using partial application together with this idea of iteration lets me write out a lot of these circuit patterns in a way that generalizes very nicely. I can use those same ideas to make it easier to reason about higher level algorithmic concepts. So for instance, if I'm writing out something like Grover's algorithm for many applications, I might want to reflect not around a bit string, but about an integer representation, and let the libraries deal with how that gets represented as a bit string. And so I can do that, for instance, by saying I want to reflect around a particular index. The register is to be interpreted as an integer in the Little Indian representation. And then I can apply, as a library developer, I can implement that by using the within apply block to get back to a case where I know how to reflect, namely the L1 state, and use the control Z operation there. And to get to the L1 state that I know how, I want to flip every bit in the register that is a 0 in the bit string I want to flip about. And I can do that by mapping 0 onto an expansion of that index in terms of a Boolean array, and use that with a classically controlled X and apply to each. When I'm done now with the reflection, the within apply block handles the adjoint part of that, undoes, and takes me back to where I was. And so I get a reflection, the reflection I want, that as a library user, I don't have to think about this decomposition into bits anymore. I say reflect about 3 on this Little Indian register. And so that makes it a lot easier to express things at a higher level in terms of how the algorithm works. And that's exactly what we do with the QML library when we talk about training. So if I look back at that train sequential classifier operation, I'm describing the high level things here, such as what is my model? What are what's the structure of that model? Where are the different controlled operations in that? What are the parameters of that model? The samples, my training samples, the different training options that I can use to control. So I get a very high level description of that training procedure in terms of the library functions and operations provided with the Quantum Development Kit. Importantly, all of this is open source. So you can go and peel back the hood and you can see how it looks. You can look at the different pieces of as you use them in your research, or as you continue exploring QML. So there's a number of different repositories covering everything from the samples to all the internals of the compiler and the runtime and the simulators through to the libraries that you've seen so far. Python integration with IQSharp, and the katas that help teach and introduce you to concepts around both Qsharp and, for users that haven't seen some of the quantum algorithm stuff, there's a lot of that content there as well. When we developed the quantum machine learning library, we did so in public and got early feedback from the community so that you can go check out pull requests as we write them and see how these features evolve and use that to understand where we're going with things and offer feedback and explore things that way. So all of this really is meant to speak to the theme that really these are tools to help you out in your research to explore quantum machine learning. And one really important piece of that Chris and I have really worked on over the years is making sure that that research is reproducible, whether that be so that it's easier for your collaborators to pick up in the research that you're doing and run things, or whether it be the readers of your paper trying to reproduce your results. So when you write things out in terms of concrete programs like we've seen so far using these high-level ideas, it makes it a lot easier for your research to be reproducible in that way. And there's some real technological components that go into that as well that I'd like to talk to a little bit. In particular, one of them is an idea that's come out of, again, classical software development that's really helpful here, of containers. So here, for instance, a container is effectively a little miniature installation of an operating system that's completely self-contained. So it makes it really easy to build and deploy new kinds of applications, especially research applications. In that when I build a container, I do so from a set of instructions that says exactly what to install in it, how to install it, and so you get a reproducible software environment along with that container. So the QDK is distributed along, part of the QDK includes images for using Qsharp as containers, and so that you can use along with, for instance, your IDE may offer the ability to run things inside a container. So for instance, here this is where I work with a quantum development kit samples, and it's a Linux prompt, it's all running bash and everything like that from a Windows machine because it's Linux in the container, and that's how I test to make sure that the samples that we distribute with the QDK work well on Linux. It's a container that has all of those Linux prerequisites folded in. So when you use a container like that, it gives you one place where you can specify your dependencies, and it makes it really easy for collaborators and readers to reuse and build on. So this is an example from the samples where we say start from IQSharp as provided with a quantum development kit, install some extra Linux packages that you may need, install some extra .NET stuff, install some extra Python packages like Qtip and Qinfer, and then you can drop back down to user, and that's a complete description of the software required for that project. There's another sample that we provide along these lines that provides Qsharp, Python, LaTeX, everything together in one template for you to pick up and use in your research. And you can check it out on GitHub. Where I find this really comes in neat is that there's a tool you may have heard of, Visual Studio Online, or as is renamed today, Visual Studio Code Spaces, that allows you to take one of these containers that you've developed and run it against a machine in a browser on the cloud, so that the whole IDE is in a browser with no installation whatsoever. And so you can use that I find that a really easy way to reuse software environments with collaborators rather than having to worry about what software everybody has installed. So since we have a moment, let me fire up. So it takes just a couple minutes to create one of these. So here I've started from one that I've already spun up a few minutes ago, but you just pointed at a GitHub repository like the one I showed a moment ago. And that repository has a description of what containers it's designed to work with. And so the the Visual Studio Code Spaces service will start up a VM against that container and drop me into it here. Let me increase that. And so what I do, for instance, I get all my LaTeX editor here. I can build, my manuscript PDF this way. That includes all of the different source code that is provided with that project. I can get my full editor integration around Qsharp so that I can run things that way, and a terminal that I can go and say, run my quantum program in either through the .NET Core SDK or with Python. And as I do so, get all the editor integration that helps me out in writing that program. So I find a really nice way to take all of these ideas that we've seen so far and make them reproducible as a tool for exploring research ideas with quantum development. So I guess I ran a little bit under. My apologies. I'm still getting used to virtual seminars. I find they time a little bit differently, but means more time to check out links and ask questions if there's any I can answer for you. In the meantime, thank you again so much for having me here.
Thank you, Chris. Yeah. I need Zoom needs like a canned applause feature. That's awkward relative to what normally happens in a seminar. But thank you very much.
No, thank you
for that talk. I have a couple questions, but I'll open it up to the audience first. Does anyone have a question? So my question was about this comment that you had about these thinking about algorithms at a higher level and how Qsharp helps enable that. And I guess my guess is that when people come up with algorithms, they kind of necessarily have that some sort of high level idea in their mind, intuition for what's happening. There's no way that they're thinking about vectors and circuit diagrams when they're developing these algorithms. Do you think that the way in which Qsharp works kind of mirrors that process that people have, or is it possible to have maybe a more visual abstract representation of these algorithms? Maybe maybe that doesn't have to be a dichotomy. Maybe they can work together.
I mean, it probably isn't a dichotomy, but it's again where I kind of fall back to classical software development thinking, and there's no shortage of different ways that we visualize classical programs. Whether it be like UML diagrams, or whether it be graphical programming languages like Scratch or Mindstorms or things like that. Most of those in an educational context, but still. And there's always a lot of appeal to that. But at the end of the day, where we always tend to come back to is languages. And I think there's a real reason for that. Like when we write out an algorithm in a paper, there's a really beautiful example of an algorithm in terms of how it was typeset and explained and everything from Andreas Gillian a few years ago, where it's, but it's pseudocode, right? It's in text, in that paper, English language description of something. And when you're writing in terms of language, it's really easy for that to be text. And that's what we've learned out of classical software development. You can go through a lot of the history of there's a really great paper from, I want to say, the early 60s about notation as a tool for thought, advancing the idea that there's this idea popular amongst the human linguistics at the time, the Saussure-Whorf hypothesis, the language you speak in affects how you think. And so there is a paper written about how that applies to the design of programming languages as well. People have been working on that kind of way of thinking about languages for several decades now. And that's something that I think we can take as learning in the quantum programming space as well, to say it's worked really well to have some of these graphical tools as aids, but it's also worked really well to have a good text-based representation, a good language for expressing ideas around our algorithms. So there's a blog post one of the members of our team, Alan Geller, wrote a little over a year ago that I just always come back to as a great example of that, as to how that affects us in Qsharp, how that affects kind of our design principles. And, right up there, the TLDR, we want to write algorithms in Qsharp.
Right.
Sorry, that was a little bit long-winded, but.
No, thank you.
I have a question.
Yeah, go ahead.
Hi, Chris. So I wanted to ask you a question
Hello.
about your machine learning, the machine learning part of your talk.
Okay.
I am still a relative newbie when it comes to machine learning. But you had this classifier, and what took me a little bit by surprise was at the end of this this process of putting this classifier inside representing it as a kind of a set of quantum instructions. You then took the output of a qubit and made your decision based on the sort of probability of receiving a particular outcome. Many quantum algorithms, or most quantum algorithms that I have been familiar with over time, calculating a probability is only when you only do that when you kind of want to study whether your algorithm is working properly or something in more detail.
Right. But
the actual quantum algorithm usually transforms the answer into a kind of the outcome of a measurement. Can you comment a bit on the difference between on whether it's more powerful or less powerful, or what are the differences between designing a quantum algorithm where the output is the output of a measurement on the qubit rather than the output of an ensemble of measurements related to a probability?
Yeah, no, and that's a good question, and I think it's certainly true that this is unusual in the sense of looking at algorithms like Shor's algorithm or Grover's algorithm, where or even something like Deutsch-Jozsa, where I get a very specific answer back and I measure that might be wrong due to noise in my device, such that I might want to repeat, but I'm not trying to measure the probability with which I got that answer.
Yeah.
But on the other hand, the classifier output in this case is actually fairly typical of variational quantum algorithms, which tend to be quite good at limiting the number of qubits you use, of degrading more gracefully with respect to noise. So it may not be what you want to do if you have a fully fault-tolerant computer with lots and lots of qubits, but it gives us some good, more medium-term applications that we can explore and use in a variational sense. Does that end?
Well, yeah, because just following on briefly. So the variational idea I understand of being you're calculating the ensemble average of a particular physical observable, and you're trying to minimize that to, for example, work out or use that as a way of bounding some sort of minimum value. How then? But again, so that this is now rather than, so I can kind of see that if you are basically trying to look for the minimum in a data set, and then as you're just calculating this ensemble, you're using that as simply as a means to get different values, and you're trying to push that down, and kind of you can zoom in as much as you like. But here you're now looking at, okay, well, it's really, I'm creating a threshold or something in this probability value, and that's the one that's what is of interest. Is there any difference in there, that sort of intuition that I can understand how this sort of classifier differs from the variational idea?
So I mean, there's two pieces there that I think are both independently worth noting. One is exactly as you say, here we're looking at the expectation value of an observable, in this case Z, and we're trying to either minimize or maximize that depending on what the actual label we're trying to produce is. So the gradient there is trying to make sure that the expectation value that comes out for each different V that I feed in matches the labels that we have. So it's an example of a supervised machine learning problem. As far as the thresholding, in terms of classical machine learning, we understand quite well that there are limits to how well you can ever actually classify data if you don't have something nonlinear. And one of the most common nonlinear things that you'll throw in is a thresholding rule. So here, the paper that describes the algorithm, here's the archive link again, goes into some nice more detail. In full disclosure, this wasn't my research, but rather, my work is implementing the QML library as part of a team. So that paper goes into some nice details as to how you can map these variational ideas onto sort of more classical machine learning ideas. And you can, in that sense, think of the quantum program that you run as many of the linear steps in a neural network, and Born's rule and thresholding is giving you the nonlinearities you need.
Okay, so in terms of the classifier, we have the idea is to basically, for some set of inputs, push your function as close to a step-like response as possible. You want to get things that are as close to either the zero or the one. Do I understand this? Is the idea that using a quantum program, you can try to make that kind of crossover boundary area sharper, or than maybe you can with a classical program, or?
So not necessarily sharper, but maybe using less resources. So for instance, this is a 2-qubit classifier, and you get this kind of a decision boundary out of, which is quite something for 2 qubits.
Okay.
And it's exactly as you say, trying to push those two apart, and there you can kind of see that in this sort of topographical map. And where things go wrong is if you have a bit of noise and one point is an outlier on one of the two classes, then it might be misclassified if you haven't given lots of room between those two classes. So there's something where, as I take gradient steps, it would want to try and push those two classes apart more to deal with that. But trying to understand exactly where we get advantage out of, trying to understand, how the cost of this compared to traditional classical machine learning algorithms, that's part of where it's really helpful to have this, where we can run against different data sets and understand what it would take to classify those. The quantum development kit ships, for instance, with 2 example data sets and the samples, this being one, the other being one of the, I forget the name of the repository, sorry, but there's a machine learning sample data set repository that has a really nice examples of wines broken down by their different properties as assessed by different sommeliers. And so that's a pretty standard one to classify into, is this a good wine? Is this a bad wine? And
excellent.
But and there might
excellent use of quantum resources.
Right, thanks.
I mean,
Chris.
it's again with the Half Moon data set a standard benchmark for understanding these classifiers before deploying them on new data sets. So, but yeah.
Right, thanks.
Thank you.
If anyone else has any questions, just unmute yourself and make a loud noise so we know that you're about to ask a question. Chris, do you have any numbers on adoption of Qsharp, like within the research community and outside of it?
I don't directly know. I mean, I've seen a few really neat papers on archive using Qsharp. For instance, on improved arithmetic decompositions and things like that, as well as ones from our own group. There's been some neat stuff in collaboration with Pacific Northwest National Laboratory here in the state of Washington. In terms of numbers of users, great way to see that is like the number of GitHub stars and things like that, where we're seeing a number of GitHub issues, where we constantly are seeing feedback from people who use and have ideas as to how the quantum development kit could be better. And you know, we take those ideas into account and we use it. Like, having been using it for 11, it started since 0.1 now, and with it at 0.11, I can say how much that feedback has really helped us make something better and more useful in research.
Great. Well, if we have no more questions, maybe Chris, could you just let everyone know if they want to say get started?
Yeah.
Where's the entry point? What's the best link?
So there's a number of links that I could suggest here. The documentation website is a great place to start. Go to docs.microsoft.com/quantum.
We're not seeing anything on your screen at the moment, Chris, if you're trying to show us something.
My apologies.
Mm-hmm.
There we go. But docs.microsoft.com/quantum is where all of the documentation from conceptual and getting started to the API references on each individual function and operation offered with the QSharp libraries. It's all available through there. You can try without installing, so that'll bring up a Jupyter Notebook instance online on Binder that you can use to get started with the quantum development kit samples. The katas are a sequence of self-paced, self-driven exercises that are now available online through Binder as well. So, you know, if you tried out back at the hackathon that you and I did, Chris, back in, was that 2018 now? But you can try online at aka.ms/try-quantum-katas. There's an external site that has a lot of really good resources that they've accumulated there, Qsharp.community. There's also a chat room that they maintain that always has some really neat questions and answers going by. And if you want to learn more about the open source, our open sourcing and everything, please check that out as well.
Okay, great. Well, thank you again for giving this seminar. Yeah, everyone else doesn't have to unmute themselves to clap. I'll do it on behalf of everyone else. So thank you very much, Chris. And
well, thank you once again for having me here.
About the QDK.
Awesome. Well, I look forward to seeing what you do with it. And thank you once again for having me here. It's been great.
Thanks very much, Chris.
Thank you. Take care.